Very good afternoon to all of you. Today we will look at design of laterally unrestrained beams, and then in the second lecture we will look at design of plate girders. Okay, so I'll just go with laterally unrestrained beams. And yesterday we saw this slide. Actually, it says that when a beam is not adequately laterally supported against lateral buckling, the design bending strength, because it will buckle earlier than reaching MP. So the design bending strength with M critical is a function of lateral torsional buckling stress FCRB, where FCRB is the critical lateral buckling stress. And how to calculate MCR or FCRB, we will see that in this lecture. Okay, so it depends on several issues. And I also want to point out that in case of beams which are bent about their minor axis, like in the second figure, you will not have any lateral buckling. But generally we don't use beams in this position, so we always use it in this position. So these two triangles actually show that the compression flange is laterally supported. Okay, and only when it is supported, it may reach My or MP, whatever. But if it is not supported laterally, if it is free to deflect in the lateral direction, it may buckle earlier, and we need to calculate at what load this will buckle. Okay, so that is the main topic of discussion today. So this shows a cantilever which is subjected to vertical load. Just to keep the load vertical, it has been hung from the tip of the beam. So basically it's a gravity loaded beam, and since gravity acts always vertical, the load will remain vertical even if the beam deflects or twists. So we find that not only the beam has deflected laterally, it has also twisted. Okay, so that is why generally it is called as lateral torsional buckling. Okay, so torsion comes in. Now we need to know why this beam behaves like this in this manner. So for this we are looking at this slide where we are, let's say we take a I section beam and we bend it with some vertical load by applying a vertical load, so it is getting bent. So you know that the part of the beam above the neutral axis, like let's say the upper half of the beam, will be under compression, and the compression will increase from 0 at the neutral axis to a high value at the extreme fiber. Okay, so this red color basically indicates the compressive stress which is proportional to distance y from the neutral axis, and the yellow color indicates the tensile stress, which is again proportional to the distance y from the neutral axis. So what happens is, if you just look at this oval part of the beam, basically it doesn't know it's either a part of a beam or it's a part of a column. And what is happening is, since we are applying compression to it in the process of bending, so what will happen is it will try to buckle like a column. Okay, and buckling in this case will be about the weakest axis. So this vertical axis is the minor axis or the YY axis, and obviously the beam will try to buckle about the YY axis. So that is what is actually happening. So we are applying compression, and as a consequence, this upper part of the beam wants to deflect in a lateral direction. Okay, so that is what is lateral buckling. Now the next thing is why torsion is coming along with this lateral buckling, because you can see here in the lower part of the figure, the upper part of the beam is trying to move out due to lateral buckling, but the lower part below the neutral axis is under tension. So it has no need to buckle laterally. In fact, it doesn't want to buckle. In fact, even if you take a bent member and you try to apply a pull, what will happen is it will straighten up, right? So this member or the lower part resists the lateral buckling. As a consequence, the upper part wants to move to the right side, but the lower part wants to remain in that position. So a consequence of this effect will be that the cross section will twist at the midspan, right? Wherever it's possible for it to twist, it will try to twist. So if the entire beam is allowed to twist from end to end, the entire beam may twist, or if the ends are restrained against twisting, then only the middle part will twist. So then the beam cross section has to undergo twisting or torsion. Okay, so that is why we are getting both lateral buckling and torsion in the picture. So now, to understand this effect or to calculate the critical buckling strength MCR, we also need to know a little bit about torsion. So I'll just go one or two slides to revise the basics about what happens when you apply torsion to cross section. Okay, so this is the same slide, and this is how we get vertical deflection downwards under the action of, let's say, the bending moment, and then the beam deflects laterally and twists. So basically there are three components of deflection. One is the delta V, the other one is the delta H, the horizontal component of deflection, and the third is the twist angle rotation theta. Okay, so there are three components that are coming in, and we need to include all this in our calculations. Okay, so the contents of this presentation is, like, you will talk about what is pure or Saint-Venance torsion and what is warping torsion. Then we'll derive, or we'll actually see what is the equation for critical buckling moment of a beam, and then what are the effects of the different parameters on the buckling strength, and how to calculate the buckling strength for a given beam. Okay, so those are the things we are going to look at. First, we'll look at what is called as uniform, basically we should call it a pure torsion, or it's also called Saint-Venance torsion. So we are going to take a circular tube, or let's say not even a tube, it's a solid circular section, and we are trying to twist it. So again, the torque that is applied from one end to the other is uniform. So that is what this says is as uniform torsion or constant torsion in a circular cross section. So basically, going back to your strength of materials equations or derivations, you know that if I apply a pure torsion to a solid circular section, it will twist by an angle theta. That is, again, we go similar to the pure bending. We make an assumption that plane sections which are plane before twisting will remain plane after twisting. So the two ends of this segment of a member will remain plane, okay, even after twisting, and the effect of this overall twisting moment that is applied is resisted by internal shear stresses which go in a circular manner, and they are zero at the center and they are maximum as you go away from the center. Okay, so this shear stress tau is actually a function of this radial distance small r, and it will be maximum at capital R. Okay, so that is the radius of the tube. So that is how a uniform torsion or pure torsion is resisted, and based on this we can derive the equation for the twisting angle phi. So here I'll just go back one slide. This phi is defined as the angle of rotation over a certain distance. So this distance is your phi. So if this length is x or dx, then it will be rotating by d phi. Okay, so that is what we are looking here, and so we get the SV. SV stands for Saint-Venance torsion. The total torsion is resisted as G into IP, where IP is called the polar moment of inertia. You know that by perpendicular axis theorem, Ixx plus Iyy will be given as Izz, which is the polar moment of inertia. In this case, it's IP, and into d phi by dz, where phi is the angle of twist and z is the length along the axis of the member. Okay, so this is the equation. Okay, so that is what we are getting in pure torsion. Okay, now let's go and see what happens when you twist open sections which are not really circular. Okay, so let's see like this. So I take, let's say, an I section and I try to twist it. So what will happen is it will twist, but apart from twisting, there will be this condition of plane section remaining plane will be violated. Okay, so I want to show it to you by just twisting this sheet of paper. I hope he's zooming on this. So look at the ends. I've just marked them a little bit black. So now I'm just twisting this paper, and you can see that one end goes inside and the other end comes out. Okay, so when I twist this section, this is an open section. I have not glued the paper. So when I twist this, one end is going in and the other end is coming out. So basically we realize that plane sections which are plane, they are not remaining plane after twisting, right? So that is what is called warping. Okay, so the warping torsion now can be resisted by the Saint-Venance torsion and another torsion called warping torsion. Okay, so and in this case most of the warping is in the flange and is related to the shear in the flange. Okay, so we'll see how it looks when we actually see. So the torsion actually is not able to go in a circular loop. So what it does is it goes like this, and then it has to come back into the web. Okay, so this shows the twisted. This is the top flange which has come down here, and this is the bottom flange. This is the web which has got twisted towards us. This part has been twisted towards us. So top flange would have been here. Now it has come down here. Okay. So in this case, the beam is free to warp, just as I showed you with the paper. The paper was free to warp at both ends. So the paper could move out of the plane at either end. Okay. So in this case, the ends are said to be free to warp. Okay. Now if that is the case, then the torsion is, you will have warping strains, but you will not have any warping stresses, and the warping torsion will be actually zero. It will not be able to take any warping. Okay. But let's say you build in one of the ends. Before that, okay, let's go to this. So this is how the stress pattern due to pure torsion will look in the flange and in the web. This is exaggerated. So in the top fiber, you'll have a shear stress going this way, and then the bottom fiber it will be this way. Actually, it will come down here, go into the bottom flange, make a loop, and come up, and then go back. Okay, so this is how the shear stresses is flowing into in the cross section. And in case you don't allow this free warping to occur, then what will happen is you are actually trying to push the end which came out back in and pull the end which went in back out, right? So that you want to maintain the this cross section as plane. Okay, so I have built in this one. So there's no scope for warping deformations to occur in this cross section. So as a consequence, what happens is warping stresses will occur. So you have to remember that whenever you prevent any deformation, the material will respond by developing stresses. So warping strains are zero at this cross section, but warping stresses will be there. Whereas at the free end, it is free to warp. So there will be no stresses. So always free ends will have zero stress. So this cross section will have zero warping stress. So what's happening is here the entire torsion now, but the torsion is constant. So we are applying a torsion T at the end, and the reaction is also T. So there is uniform torsion, but what is happening is at this end the entire torsion is taken by Saint-Venant's pure torsion, and at the other end the entire torsion is taken by warping torsion. So what is happening is the warping torsion is zero here, it becomes maximum at the fixed end. The Saint-Venant's torsion is maximum here, it becomes zero. But when you add these two at any cross section, they will add up to the equilibrium equation, that is TA. The total torsion will be TA. Okay. So this is what is happens when warping is prevented. So that gives you some extra stress. So this also contributes to the resistance of this I section to twisting. Okay. So if you prevent the ends from warping, that will add to the resistance of a open section to twisting. Okay, in the form of warping torsion. Okay. So with that as a background, we will look at what happens when you take a beam and apply equal and opposite bending moments. So my bending moment is constant throughout the length of the beam. So you are actually applying equal and opposite moments at the two ends, and we just make some assumptions for this ideal or basic case. Okay. So I'm just showing you this figure here. So this is my I section which is bending, and as a consequence it is laterally deflecting and twisting also. So at the ends of the beam, what has been done is these two vertical guides have been put. So they prevent free twisting of the end. So torsion is restrained at the ends, but it is allowed at the center, and I am applying a basic M moment M throughout the length of the beam. Okay. So under this constant movement, so that is called the ideal case. So if I take this, I want to know at what bending moment M critical this beam will laterally buckle. Okay. So if it's an ideal case, we say that the beam is undistorted, then it is under elastic conditions. So there is no inelasticity we are assuming anywhere to occur. Then loading is by equal and opposite moments in the plane of the web. That is, the bending moment is constant throughout the entire length of the member, and then there will be no residual stresses. The beam is free from any residual stresses. Ends are simply supported vertically and laterally. So as I said, by putting those two guides, we are simply supporting the ends in plan. So this one. So the ends can rotate in plan, but they can't move away in plan like this. They can't deflect in plan. Okay. So that is what we are talking about here. So the bending moment at which such a beam, ideal beam, fails by lateral buckling when subjected to end movements is called its elastic critical moment. So when, as I go on increasing M, when M reaches MCR, it is going to have lateral torsional buckling. Suddenly it will buckle, similar to the column. In a column, if I take a column, I put an axial load, and exactly when the axial load reaches P critical, it will suddenly buckle, right? But we don't see this kind of behavior in real columns because they are already imperfect. They actually violate most of the assumptions which are made by Euler. So similarly, in real beams, the beams are never perfectly straight. Okay, they have a slight bow because of the rolling process by which they are fabricated. They may not have, they will have significant residual stresses again because of the rolling process. The loading may be anything. It need not be exactly uniform bending moment. It could be a triangular bending moment or any other shape of the bending moment. So all those things we'll see how to adjust after we derive the equation for this M critical. Okay. So similar to the column, you assume the deflected shape, and then based on that you can work out what is the internal movement of resistance to the bending, and then that we find is now consisting of basically three components or three rigidities. So basically MCR is the torsional resistance, square root of torsional resistance plus warping resistance. So which is given by pi by L, where L is the span of the beam, E into Iy. Iy is the minor axis moment of inertia of the beam, Gj, where J is called the torsional constant. So I'll just go back 1 second, but yeah, here we saw, let's compare this equation for the circular section. ESV is IP into G. So basically GIP into d phi by dz, where IP was the polar moment of inertia. But that IP gets replaced for an open section, as you can see in this slide, by J. Okay. So J is called the torsional constant. It is proportional to the sum of the width and cube of the thickness of each component plate. So if it is an I section, width of the flange, top flange, into thickness cube of the top flange plus width of the, basically in this case depth of the web into thickness cube of the web plus width of the bottom flange into thickness cube of the bottom flange. So all these three if you add, you will get sigma BT cube, and this C is a proportionality constant. So J will be calculated as sum of BT cube of the component plates. Okay, so that is how we get J, and Gj is called the torsional rigidity. Okay, so that is the quantity which gives the resistance to twisting. Okay, and E gamma, where capital gamma is called the warping constant, and E gamma is called the warping rigidity. Okay, of the material cross section. So it's basically a function of these two, and you can see this as a negative sign here. So warping rigidity, if it increases, then if it reduces, the beam is easier to twist. Okay. So there's nothing to worry about in this equation or whatever. It can be derived, but what we need to understand is the physics of the problem, and that is that beam buckling is quite similar to column buckling. In column buckling, you apply P as an axial load, and at the deflection again is perpendicular to the direction of the load, so it laterally buckles and fails, and that is called P critical, the buckling load for an ideal column. For a practical column, we know that due to imperfections, residual stresses, etc., the minute I apply a small p, it will slightly buckle. Okay, and as I go on increasing the p, the column will buckle more and more, like similar to what you do when you hold your ball pen refill between two fingers and you press, it buckles. If you press little more, it buckles. If you release, it comes back straight, right? So those kind of that kind of behavior is what we see in real columns. So in beams also same thing. Ideal beams, we derive the MCR based on the equal and opposite moments M applied. So here we note that we derive the equation for P critical based on equal and opposite forces and certain end conditions. Let's say if both the ends of the column are hinged, then P is given by pi square EI by L by R bracket square. So, and then when you have other end conditions, we want to relate it to this particular standard case. So we bring in the concept of effective length of the column. Okay. So something similar we'll do for the beams. We'll derive the equation for this standard case, and for that we will modify when you have non-standard bending moment diagrams. Okay. So that is what we are going to do here. And So the strength curve for an ideal beam can be shown like this. So if I use a lambda, which is L by, in this case it will be RYY, the minor axis radius of gyration of the cross section. That gives me lambda LT, or the slenderness ratio for lateral torsional buckling. If I plot the moment capacity against that, for beams which are very short, or which have a fairly high lateral buckling resistance, they will fail by reaching MP. Okay, but for beams which have a large slenderness ratio, or they have a low capacity for lateral torsional buckling, they will buckle at the elastic buckling moment, MCR. Okay, so as we bring down, there will be a critical slenderness ratio where the transition will occur from buckling to yielding, and this part of the curve below that is not valid. Okay, so although the equation gives you that, so we say that MCR has to be always less than MP. It cannot be more than MP. Okay, so this is for an ideal case. For practical case, of course, we know that it will be somewhere below this ideal case due to imperfection, and that will affect maximum at intermediate slenderness range. Okay, so this is the same strength curve in a non-dimensionalized form, where the lambda is now written as Fy by FCR, square root of that. So when lambda is greater than 1, it will buckle and fail. When lambda is less than 1, it will yield and fail, right? So the y-axis will be in this case MCR by MP. Okay, so we have non-dimensionalized both the x and y-axis. Okay, so this is how the strength curve will look for a real beam. We'll come back to this. So this is the basic equation for lateral torsional buckling, but we can't use this directly because real beams are imperfect, right? So we need to go back and assess the degree of imperfections, the degree of residual stresses, etc. And the real beam will have a buckling curve which will be much lower than this. So even for slenderness ratios less than lambda c, it will have MCR which is less than MP. So the curve will go somewhat like this, which is what is shown in this figure, and we need to get this curve empirically. Okay, so that is another part of the problem. Okay, now what are the other factors which affect lateral torsional buckling? The first is the similar to columns, you know that column buckling is affected by the effective length, right? So in this case, the effective length is the distance between the lateral supports to the compression flange, because that is what is buckling. So that is my effective length for lateral torsional buckling. And then it also depends on, the effective length also depends on the restraints at the ends and at intermediate support locations, or the boundary conditions. So that is one more thing. And unlike in columns, basically these are the two factors which affect, but in beams some more factors are affecting. That is the type and position of the load, then the moment gradient along the unsupported length, the type of cross section, whether in columns of course the entire cross section property is brought in by one single factor, that is the least radius of gyration, right? So you say L by R min is the slenderness, and buckling strength will be a function of the slenderness of the column. Okay, but in beams even the shape of the cross section will matter. Okay, because warping etc. would depend on the shape of the cross section. Then of course beams can also have non-prismatic cross section. We have seen yesterday that sometimes we may want to design tapered or stepped beams. Then of course material properties, distribution of residual stresses, imperfection in geometry, and eccentricity of loading. What I mean by eccentricity is if the load is not exactly on the web, if it is on one side, let's say I have a beam and I have a slab supported only on one side, then my load will be slightly eccentric to the center line of the beam. So then again I'll have some twisting, right? So those are the full list of factors which affect the lateral buckling strength of beams, but they are rather difficult to incorporate in any simple calculation. So we cut it down to, let's say, about 4 typical issues or factors. The first one is the support condition. So what is the effective unsupported length? So I've just shown here, this is the elevation of a simply supported beam. Of course I should have shown a roller here. So one hinge, one roller, and this is the plan of the simply supported beam. So it doesn't really matter what is the end condition in elevation. what matters for lateral buckling is what is the end condition in plan. Okay. So by putting just two rollers like this, I am saying that deflection at either end is prevented, but rotation in plan is allowed. That's why this beam is able to buckle laterally in this manner. Okay. But if I suppose built in this end plan, that is I put two more rollers, then this beam has to come out essentially in a straight line, and away from the support only it will be able to buckle. So this will become like a fixed end condition in plan. Okay. So that will reduce the effective length of the beam for lateral buckling, right? So that if you have, for example, both ends are fixed, then my effective length may become L by root 2. Okay. So that is the effective unsupported length based on the support conditions. Next is the level of load application. Let's go back to the I section here, or even little bit before that, where I showed you how lateral buckling occurs. So I have come to slide 4, and in slide 4 you can see if I apply the load on the top. Okay. So essentially I am applying the load here, and the resistance of the web which is offered as a shear against this load, if you add it up, it will all be vertical. Okay. And it will pass through the shear center of the cross section. So in this case for I section, the shear center is at the middle. So the resistance here, the load will be little on the right hand side. So what will happen is, if I apply a load on the top flange, my eccentricity between the load and the resistance will further tend to twist my cross section. Okay. So as it is, the beam is trying to laterally buckle. Now this level of load application is further aggravating the situation and making it twist even more. Okay. Whereas imagine if I had suspended something from the bottom flange, instead of applying the load on the beam from the top, I hang some load at the bottom. So then my load is downwards here, the resistance is still upwards here. So I have a clockwise restoring movement which will partially compensate for this lateral buckling. So the beam will be able to take little bit more of the bending, okay, without significant twisting. So the level of load application plays a major role in most problems. And in structural engineering, generally we tend to apply loads on the top of the beam, right? Very rarely, like when you have something called an underslung crane, then you will apply a load at the bottom of the beam. Or if you are having some secondary beams bringing the load, then the load level may be different. But generally the load will be at the top flange. So the effective length for top flange loading will again be different, but then that may be difficult to consider. So what the code says is that you increase the effective length by 20% if the load is on the top flange. Okay. So level of load application, if it is on the bottom flange, it's called stabilizing. If it is on the top flange, it's called destabilizing. Okay. So that is the major factor which affects the critical buckling strength of beams. Okay. Then the type of loading, uniform or movement gradient. The standard case that we looked at was this, that is I have applied uniform movement at both ends, which means my bending moment is uniform from one end to the other. So but in real beams, like let's say if you have a UDL, I'll have M max in the middle and 0 at the ends. And anyway, the ends are not laterally buckling, so even if the moment is 0 there, it's not going to matter. But the M max will be only at one cross section in the middle. When M max reaches this MCR for this case, the beam may not really buckle, or it might not appreciably buckle, I should say. Critical buckling strength will be slightly different. So now the question is how to consider the movement gradient. We'll come back to that later on in the subsequent slides. So that also matters. Okay. Then of course the most important issue is the shape of the cross section, and in that we can say that it doesn't matter if the I section is a little bit more prone for warping or less prone for warping. What matters is it is prone for warping, right? So what I'm trying to classify is sections which are open, like I sections, channel sections, etc. They are prone for warping and they are called open sections. So they will have significant lateral torsional buckling, or the buckling strengths will be fairly low. And if the sections are closed, like in a circular tube or a rectangular tube, whatever, so then there would be hardly any warping. And also note that a rectangular tube has two webs. Okay, it's like having two webs and two flanges. So the two webs will contribute significantly even by the AR squared of their their property to IYY. Okay, so IYY will be apart from let's say we neglect their moment of inertia about their own axis, but when you shift by parallel axis theorem, IYY will be approximately 2 times IYY of the section about its own axis plus 2 times AH square, right, where h will be the distance of the web from the center line. So that also contributes. So EIY will also be high, and as a consequence, box sections will not laterally buckle, or they will not have the problem of lateral buckling, or they'll have a very high lateral buckling strength which will be above the MP. So as I go on applying load, they will buckle, they will yield at MP and fail. So there is nothing to worry about lateral buckling if you are using closed sections. Okay, so that is what matters here. Okay, so given that background, we'll see how the code helps us to calculate the lateral buckling strength. So the code says basically if your the factored bending moment M should be less than the design bending strength, and if the beam is laterally supported, we saw yesterday how to calculate the design bending strength. But if the beam is laterally unsupported, that is covered in 8.2.2, instead of beta B ZP into Fy, now the code says you use FBD, the design bending strength. That is how stress, that is how we have to read this. So the design bending stress FBD is obtained as a reduction factor chi LT for lateral torsional buckling into Fy by gamma m naught. Okay, so this chi LT incidentally looks quite similar to the function that we were using for buckling of columns, the design compressive strength in actually loaded members. So it is 1 upon phi L square root of phi LT plus square of 1 upon phi LT plus square root of phi LT square minus lambda LT square, where lambda LT is defined as the slenderness ratio for lateral torsional buckling, and phi LT in turn is given by this formula where alpha LT and lambda LT are coming in. So already we know lambda LT, but alpha LT is now defined as the imperfection parameter. And if you remember column strength curves, there are 4 column strength curves A, B, C, D. So similarly for beams, there are now 2 beam strength curves depending on the imperfection and the residual stresses. So both are clubbed into the single factor alpha LT. So for rolled sections, the value is 0.21, and for welded sections, the value is 0.49. Okay. So as you increase alpha, the chi will come down actually. Okay, and as a consequence, the strength FBD will come down. So basically, what we are saying is a rolled section will buckle at a lower MCR than a welded section will buckle at a lower MCR than a rolled section. So that is what the code tells. Now this lambda LT we saw is a non-dimensionalized slenderness parameter. So how to calculate this is basically beta B ZP Fy divided by MCR, where MCR is the theoretical critical lateral buckling strength of the beam. Okay, so MCR is basically given, this is same as the formula that I showed you before, where the first term was the Saint Venance or pure torsion, and the second term was the warping torsion. The code uses IT instead of J and IW instead of capital gamma. So that is the only difference in notation. So the code gives you that same formula for a general cross section, and it also goes ahead and gives a simplified formula for what are called monosymmetric sections like I sections, where you have a single axis of symmetry, and as a consequence the shear center coincides with the vertical YY minor axis. Okay, so for that, this formula, by substituting the properties of the I section, I gamma, IY, etc., IW, IY and IT, these 3 properties, we can simplify it to this formula, where what you need is only h by Tf, where h is the center to center distance between the flanges and Tf is the thickness of the flange, and Ry you can get from steel tables for a rolled section, this is the minor axis moment of inertia. Iy also you can get from rolled steel tables, that is the minor axis moment of inertia. This is the radius of gyration about the minor axis, and then beta LT is a factor which takes into account the non-uniform variation of the bending moment. Okay, so this is what is given in the 8.2.2.1, And there is also an appendix in the code which gives the elastic critical moment for in more detail, right, for various sections. So how to calculate IT and IW? If you want to refer, you can refer to the appendix F. They have given the formulas of how to calculate IT and IW for a typical I section. Okay. So coming back to the beam strength curves, substituting those two values of alpha, and if you calculate chi as a function of lambda, you will see that the graph goes like this. So for the rolled section, this is the graph, the blue dashed line, and for the welded section, this is the orange continuous line. Okay, so this is how the graph will go. So anything beyond, let's say, lambda of, I would say, even 1 or 1.2, the lateral buckling will be critical, and it would be economical to give some degree of lateral support or to change the cross section so that the chi value is not below 0.5 or 0.4, because if it is going much below this, then you will not get an economical design. Okay, so efforts are generally made to ensure that the lambda is generally less than 1.2, so that I get a chi value of at least more than 0.4 or 0.5. Okay, so that is what is done. Coming to the type of loading, that is whether the bending moment is uniform or non-uniform. What the code says is that you can convert a non-uniform bending moment diagram like this into a equivalent uniform bending moment diagram by a simple formulas given in the code. So in this case, let's say if I have a triangular bending moment diagram for a point load here, this will be WL by 4, right? M max will be WL by 4, and if I apply a beam with M max, it will buckle at as per the basic case at some M critical. Now that M critical will be slightly higher for this beam because these sections are not subjected to M max. So what we are doing is we are calling equivalent uniform moment, which we can call it as small m times M max, which will be the average equivalent uniform for a basic case, at which this basic case and this non-standard case will buckle at the same M critical. Okay, so that is what the code tries to do. It gives you the equivalent uniform moments for different load cases. Okay, so one simple equation looks like this. As I said, the equivalent uniform moment M or M critical is equal to small m times the maximum bending moment in the span of the beam, and this small m is a function of a factor called beta, where beta is the ratio of the minimum bending moment to the maximum bending moment. The code uses Greek letter xi for this, so it doesn't matter. So xi is the ratio of the minimum bending moment to the maximum bending moment. So if my bending moment is varying like this, maximum here and minimum here, xi will be m minimum by m max. Okay, so that will be the value, and that I substitute to get m, and then with this m, if I multiply this m max, I'll get an equivalent uniform bending moment diagram for which the beam will buckle at the same m critical as this beam where the bending moment diagram is not uniform. Okay, so that is what it is. Now this m minimum is sign sensitive, so if it is in the same direction as m max, let's say you assume upwards positive, sagging positive in this case, so both are positive. But in this case, this is hogging, this is sagging here, so m minimum is to be taken as negative. Okay, so if I take m minimum as anything less than 1 and m max is positive, beta will be less than 1. So beta can vary from -1 to +1, and consequently the m will have to be calculated. Okay, so now how this m varies with reference to xi, we'll see later. Before that, we are also looking at the effect of the shape of the cross section. Okay, so in terms of the cross section here, what has been plotted is m critical of a given cross section divided by the m critical of a box section of similar depth d. Okay, so if I have a box section, I'll have the largest lateral buckling bending strength, so that is taken as 1. So when you divide the same value by the same value, it becomes 1. With reference to 1, how much reduction I am getting due to the shape of the cross section. So if it is a, let's say, an I section which is slender and somewhat slender. So it will have only about, let's say, on an average less than 0.1. I can say this is around 0.8. Note that this is a logarithmic scale. So this will be around, let's say, 0.7 or 0.8 of the I section. Okay, so that is what from 100% it comes to about 0.08. So that is, it comes to only about 8% of the strength of a box section. If the I section is very deep, as they use in plate girders or some industrial buildings, then it can come even much less. It can come to only 2% of the full strength. And if it is just a single vertical plate without flanges, then it is very, very low. Okay, so it is like almost 1/1000 of the strength of a box section. Okay, so that is how it is going on reducing. So obviously these sections will not be preferred when lateral buckling is an issue. So one option is either even if we give lateral supports at some points, their buckling strength may not improve much. So we need to improve on the cross section. Okay, so that is why in some large span beams, when lateral torsional buckling is an issue, they go for sections like box sections. Okay, so effect of type of cross section plays a major role in calculation. What the code is giving us, most of the equations are for I sections. So for a typical I section or a H section bent about its major axis, the properties J, W, S and gamma, all these are given here. So you can use this to calculate the these two values. Basically J and gamma is what you will need. So this is written as IT, the torsion constant. This is written as IW, the warping constant in the code. So if you can get these two, where B is the width of the flange, T is the thickness of the flange, and D is the depth of the web, and small t is the thickness of the web. Okay, so that is how we can calculate. Now some other codes give you some other equivalent uniform moment factors CB or modification factors CB, with which you can multiply M max. Okay, so this CB is nothing but our small m that we just saw. So that gives you an equation in terms of various m values. We'll just skip that. But basically the small m varies with xi somewhat like this. So if xi is -1 to around -0.5, it is constant at 0.4, and then it goes on increasing. And when xi becomes 1, m also becomes 1. Okay, so that is how this plots. This equivalent uniform moment factor diagram is also given in our code IS 800, and as I said, the maximum moment is denoted by m, the minimum moment is denoted as xi times m. So whatever may be the value, if I divide this by this, I should know what is xi. Okay, so xi will go from -1 to +1, and for uniform loading, the CMLT factor is given as 0.6 plus 0.4 xi, but always greater than 0.4. So basically that 0.6 plus 0.4 xi is equation for this line, and it is not valid below this value. So 0.4 is the minimum value that is to be taken. Okay, and if the bending moment diagram is like this, then how to calculate the xi factors are given. Okay, so now having said this, so as far as possible we should, if possible, try to avoid lateral buckling. But sometimes what happens is your beam may be laterally unsupported during the construction stage, and only after the complete erection is completed, then it may have lateral support. So sometimes we may have to analyze some beams for lateral buckling during the construction stage. As an example, I'll give you, let's say we decide to use I section beams as in a composite construction, and then we use that beam as a support to put the formwork, and then we cast the slab, a reinforced concrete slab. So once the reinforced concrete slab hardens, there will be something called shear connector between the beam and the slab. So once the slab hardens, it will give what is called as a continuous lateral support to this beam, right? Yesterday somebody had asked the question, what are the practical cases where how lateral support is given to beams. So once the slab has achieved its strength, it gives a continuous lateral support to beam, and the beam will not laterally buckle. So you can consider the beam as laterally supported beam. But before that, under the weight of the wet concrete, you have to consider it as a laterally unsupported beam. Okay, and then you have to check that this will not laterally buckle. In case you find that it is buckling laterally under the weight of the wet concrete, you may give temporary lateral supports. Okay, so those are possibilities. What are the other places where you may get lateral support, right? Like, so what they do is, if you find that two beams which are running parallel to each other, both are laterally unsupported, and I want to support them, I may want to give plan bracing, okay, between the two beams. So this plan bracing will ensure that the beams cannot deflect laterally and they get supported. Okay, so this is called discrete bracing. That is, it's not continuously braced. So what we do is basically we take L as the original length for lateral buckling, and we find MCR is much less than MP or MY, whatever. So the beam is laterally buckling at very low strength. So I want to increase the strength. So first I'll give one support at the middle and reduce my effective length to half. So now for this reduced effective length, I'll again calculate MCR, and if it is still lower than MY, either I can use that MCR as the design strength, or if I want to increase, I'll have to give additional lateral support, right? So that is how we have to go on giving extra lateral support until the MCR goes above MP, and then we can say that the beam is now laterally supported. Okay, so that is one part. So that is called discrete bracing, and this discrete or continuous bracing, whatever it is, has to be given to the compression flange, at the level of the compression flange. So that becomes another issue. So sometimes it may not be possible to give it to the compression flange. So what they do is they give it to the tension flange, and then they connect the compression flange to the bracing somehow. Okay, so then it is the compression flange gets braced. Okay, we'll see one such case. For example, in a industrial roof of a PEB or some such industrial building, what happens is the beam carries the weight of the purlins and the roof sheet downwards. So under downward loading, the top flange is under compression, and the purlin and sheeting along with roof bracing will give lateral support to the rafter. Okay, so but then when wind load is acting and lifting the purlin and sheeting upwards, then what happens is the rafter also gets an upward force, and then the top flange, the bottom flange goes into compression, right? So now how to give lateral support to the bottom flange? So what they do is they give something called fly bracing, where the bottom flange is connected to the purlins on both sides. So there will be a small member which connects the bottom flange of the rafter to the purlin, and that gives you the lateral bracing required. Okay, so if you want me to show, let me just go to a cross section of I section. So if I want to brace the top flange, I can directly between two parallel beams, I can give some bracing like that in plan. But then if I want to brace the bottom flange also, so what I may have to do is, okay, let's use this as the I section. From the bottom flange, we will give a member which goes inclined and gets connected to the purlins which are running transverse to this beam, right? So there will be a member coming from here, coming inclined and connecting to the purlin at the top flange level. So both sides also we can give. That will give the lateral support. That is called fly bracing in an industrial building. You might have seen it in many photographs. Okay, so that is the other type of thing. Then bracing should be of sufficient stiffness to produce buckling between bracing. So if bracing is very weak, then the beam may still buckle by pushing the lateral brace away, right? So that means it is not effective. So the bracing has to have some stiffness and some strength. So the code says that each brace, lateral brace, should be able to take at least 2% of the force in the compression flange, right? So the force in the compression flange can be taken as area of the flange into Fy or Fy by gamma m naught, right? So that is my Tf, force in the compression flange. So 2% of that this bracing should be able to take, and that is how we design the lateral brace. Okay, so that is how it is done. Now we proceed to gantry girders. So gantry girders are basically girders which span between movement frames or between the columns in a industrial building, and they support a rail, and the crane runs on these rails, right? Basically the crane has two rails on either side, and it runs on this rail. Okay, so the gantry girder generally becomes laterally unsupported because except the columns there is no other place from where you can give lateral support to the gantry girder. Okay. So what is done is quite often the gantry girder is found that if it is a deep I section like this, it may laterally buckle, and then we want to increase the capacity, right? So what they do is, like this green line, you can put an inverted channel on top of the I section. So as a consequence, what you are doing is you are actually increasing the IYY, because the channel has a thick flange. As I said, similar to a box, this area of the flange into this distance square will add up to the IYY, and as a consequence the lateral buckling strength may go higher, okay, than what is coming as a design bending strength. Okay. So what is happening is, in this case the channel and the I section, they are welded together somewhere here, but still the entire section is an open section. It is not closed in any way. So it is going to warp and it will not be very strong in torsion. But then since IYY has been increased, it gives a better performance than a simpler I section. Okay. So that is the one problem. Otherwise we can go for a solid box section, in which case if you put the rail in the middle, then the top flange may bend. So what they do is they put the rail on one of the webs, so that the load comes directly on the web, so the flange will not bend, and there will be eccentricity of loading, right? So as the wheel load comes here, there is some eccentricity. The CG of the cross section is here, YY axis is here, but since the box is very good in taking the torsion, so that extra torsion which comes due to it will be able to take. Okay, so that is another way of designing gantry girders. So one issue in gantry girder is basically it's nothing but a simpler beam, a simple beam, but it is a laterally unsupported beam. So you have to design it quite often as a laterally unsupported beam, and when it supports a crane, then it's called a gantry girder. So that is the only one part of the problem. The other issue is with gantry girders is when the cranes operate many times, there could be some fatigue coming, okay, on the gantry girder. So that is a separate issue. We are not going to go into the details of fatigue design, etc. That is covered in section, I think, 13 of the code. But we also want to know how to give lateral support to the gantry girder so that it can take the twisting, right? So, so look at this figure. This is my gantry girder, and this is a sort of a stepped column which is battened, right? So typically for running when you have a gantry girder, the column is made up of two I sections which are laced or battened together to make a single section, and one of the I sections is terminated on which the gantry girder is supported, and from the other section which goes to support the roof, some lateral support and torsional support can also be given to this girder. Okay, so that is one way of designing. The other way of designing is, instead of only supporting at the location of the column, I give a truss running like that in plan. Okay, in 3D if I have to show it, will go like this, between one column to the next column. So an entire truss is put which is horizontal, and that gives lateral support at various points to the gantry girder. Okay, so that can also be done. This truss is sometimes used covered with some plate and used as a walkway to inspect the crane, etc., etc. So that, or it can be used to support the cable trays where the cables are put, etc. Okay. The other issue with gantry girder is when the crane lifts the load and tries to move, it gives a sort of a jerk which is coming on the gantry girder. The gantry girder has to be designed for both vertical and horizontal impact, and this is done by considering what are called impact factors. Okay, so let's say my gantry girder has a capacity of 10 tons. So let's say out of 10 tons, when the crane comes to one end of the building, then about 80% of the load will go to the gantry girder nearby, and the other 20 will go to the other gantry girder in the opposite side. So this 80% of the load will be, if it's a 10 metric ton crane, 8 metric tons will come as a load on the crane. Okay, that's a vertical load. So now if it is what is called as an electric overhead traveling crane, for such cranes it says that you should add an additional 25% of the static wheel load. So 8 tons is the total wheel load coming. So it will become 8 into 1.25. Okay. So that much load you have to design the gantry girder for. Now that is what the code is telling, to take care of the impact coming when the crane is lifting some weight, right? So if you have if the crane is lifting that 10 ton weight and it has a jerk, so an extra 25% load will come on the girder. Okay, so that is what it is. This is for vertical loads. For the same crane, for horizontal loads, it says that if it is 8 ton as a vertical load, so 10% of 8, right, that will be 0.1 into 8, that will be 0.8 metric tons, has to be taken as a horizontal force coming on the top flange of the gantry girder. So that is the second criteria. So these are called impact factors. So basically we multiply the wheel load by these factors 1.25 or 1.1 and so on, and we design the gantry girder for those loads rather than just the loads. Okay, so so those are given in the code. So with that I conclude. Unrestrained beams loaded in the stiffer planes will undergo lateral torsional buckling, and we need to calculate that and verify the safety. The prime factors that influence buckling strength of beams are unbraced span, cross-sectional shape, type of end restraint, and the distribution of the bending moment over the span. A simplified design approach is given in the code, where it takes into account the unbraced span and the level of load application by just a single number like 1.2. The cross-sectional shape is automatically taken care when you calculate the IWIT and IYY values. The type of end restraint is to be taken into account. So based on that we may vary the effective length, and the distribution of moment is taken care of by equivalent uniform moment factors, which are given in the table. So that is what is the approach given in the code. For behavior of real beams, cantilevers and continuous beams, sorry, this we have not gone into it, we will leave it, but basically real beams we use an empirical equation for lateral torsional buckling. Cases of monosymmetric beams, we can use a simplified equation, and unsymmetric sections also we have understood what will happen. Okay, so if you have any questions with reference to the theory, you can ask. I'm just waiting for the questions. Maybe some people are typing it out. I'll give a minute. Okay, it says equation for MCR has got a negative sign. Can you give a reason for that? I'll just go back. Which MCR equation? Let's go to the equation given in the code for MCR. Yeah, this is the equation for MCR. I don't see any negative sign in this equation, right? So basically it is, I think, the St. Venant's torsional resistance plus the warping torsional resistance. That is how the equation should. I think the previous slide probably there is a typing mistake. So in this case there is no negative sign. Click this, slide 16. Oh yeah, that, I think that should be a positive sign. That it is not a negative sign because this is plus, so it should have been a plus sign there. Another question is whether increasing the thickness of flange or web will have more resistance against torsion. It will nominally increase the resistance because your J is sigma of BT cube. So obviously it's T cube, so that part it will definitely increase in some sense. But for torsion, I mean, general practice is to try and increase IYY by, as I said, putting a channel inverted on top of an I section. So those sections are commonly used, or a box section and things like that. But open sections, they do have limited torsional capacity. Okay, so you can of course increase T because it's proportional to T cube, so it will have considerable effect. Difference between prismatic and non-prismatic members. Basically, let's say yesterday we were looking at deflections of beams. So if I want to calculate deflection of a non-prismatic beam, I'll have to first calculate the deflection due to the bending of the one part of the beam and then the deflection due to bending of the other part of the beam, like that. So here also it will have to be tackled in that manner. But what I can tell you as a simpler alternative is, if you have a section with, let's say, within the middle 1/3 of the beam, so, and you have reduced the section after that, so you can calculate the lateral buckling resistance as for a section for the middle 1/3 of the beam. So you can assume that the middle 1/3 of the beam is continuing as prismatic up to the end, because that is where lateral torsional buckling is going to be significantly coming, right? So you can make approximations like that. Okay, so that is a valid approximation. So I don't expect the middle part of the beam to be smaller than the end parts. So generally that is not done. So that issue will not come, and you will fairly get a approximate estimate of the MCR value. So that is possible. Plate girders are defined like this. They are generally built up sections, because the rolled sections don't have deep thin webs, so that doesn't arise. So basically, when you fabricate your own section with a deep thin web and put the flanges farther away, and your web becomes susceptible to buckling in shear. Okay, that means its d by t value is greater than 67. Then it is known as it is defined as a plate girder. Okay. So now, why would somebody do something like this? Is simple. When you have a large bending moment, or when your beam design is governed by deflection, okay, I need a large moment of inertia, right? So even for a large bending moment, the farther I put the flanges, the less area of flange I will need. So look at it this way. Let's say the bending is resisted by only the two flanges predominantly. So what happens is, the top flange has, let's say, compression, the bottom flange has tension. This C and T form a couple, right? So C and T into the distance between the flanges gives me the moment of resistance of the section. So rather than increase the flange size, make it wide or thick or whatever, that is increasing the area of the flange. If I increase the lever arm, then what happens is, I will need a smaller and smaller flange to take the same bending moment. Okay, so I'll get an economy in the design. So when the spans of girders go very high and deflection starts governing, like in, let's say, in an auditorium or some commercial building where I need a very large span beam, or in industrial buildings. So what people do is, they fabricate their own section using a deep thin web, and the web is generally, the shear is not so high, so it can take the shear, but then it becomes susceptible to buckle in shear. So then it's called as a plate girder. So plate girders are very commonly used in industrial buildings, in commercial buildings, and in bridges. So they are in railways, they use a lot of plate girders to cross underground roads or rivers or whatever, right? Sorry, below the railway line, roads or whatever. Okay. So the plate girders are basically of three types. First is the unstiffened plate girder. Basically, it's nothing but an I section with a top flange, bottom flange, and a web plate. And there are no stiffeners used anywhere. So we need to check whether this girder will buckle in shear. And if it buckles, then one way of increasing is increase the web plate thickness, but that is not a economical solution. So we provide what are called intermediate transverse stiffeners, ITS, okay, which are provided to prevent web buckling and strengthen the web from buckling in shear. So those are called transversely stiffened plate girders. Okay, so that is one thing. If the girder becomes still more deeper, as in some bridges and all, then we may also provide what are called longitudinal stiffeners in the compression part of the web, because due to bending there will be some compressions coming in the web also, and as a consequence the web may buckle out of its plane. Okay, so to avoid that, this longitudinal stiffener is provided generally fairly close to the upper flange, let's say at 0.1 times D or 0.2 times D from the top flange, and that is called as a longitudinal stiffener. Okay, so then it's called as a transversely and longitudinally stiffened plate girder. So we have three types. So basically this is just a classification. We will be designing generally the middle one, plate girders with stiffened webs. Okay. So this is a typical photo of a plate girder with stiffened webs. So these are the stiffeners which are provided, and note that the spacing of stiffener is high in the middle and becomes low in the ends. This is because shear is practically zero at midspan. So there is no question of shear buckling, and as I come closer to the support, the shear increases. So I'll provide closer stiffness. Okay. So this is one way, but generally in many girders, the stiffeners are spaced at equal intervals in one part of the towards the end of the beam girder, and the middle part is the spacing is varied. Okay, so that can also be done. So that depends. Now, if you have a wheel load like a vehicle moving, so if the vehicle is in the center, so whatever shear it produces, that has to go to the end, right? So shear will be constant from here to here. So we may want to keep the spacing equal. Okay, so that also is a possibility. Now the first question is why and how web will buckle in shear. Okay, so what really happens? So basically, let's look at this, or let's look at this. This is basically a web where the load has been applied here. This is supported here, so reaction is here, and as a consequence of this load, we have vertical shear in the web. This is the reaction, and this is the load action. So we have a, let's say, a clockwise shear in this part in every vertical section of the web. Okay. Now, whenever you have a shear like this on a rectangular element, okay, so these two forces are not collinear. There is a gap between them. So this web will try to rotate, or as a rigid body, this plate will try to rotate, right? So to avoid that, complementary shear sets in. So for equilibrium of this element, you end up getting complementary shear, and under the action of the vertical and the complementary horizontal shear, you find that one diagonal. So this vertical force has a component along this diagonal. Similarly, this horizontal force has a component along this diagonal. So the two add up and you get one diagonal goes under compression, the other diagonal goes under tension, right? So this same force will have a component. If I draw it like this, I'll have a component which will be pulling it away and downwards. So those are the two components of this vector. Okay. So the other diagonal goes in tension. So what happens is I have the shear stress Q and one of the diagonals is under tension, the other diagonal is under compression. As this Q goes on increasing, this diagonal which is under compression suddenly buckles because it is a thin plate. So its moment of inertia about its center thickness axis is very low. So it will buckle out of its plane, right? As you can see here, the plate buckles out of its plane. Okay. So this is what happens. So in the pre-buckling stage, requirements of equilibrium inside an element result in generation of complementary shear stresses, and the fact that you have complementary shear stresses leads one diagonal in compression and the other diagonal in tension. So this is called a pre-buckling behavior, and this can be analyzed by normal elastic analysis. Okay, and we can get what is the principal stress in this direction, etc., etc. This is an unbuckled shear panel, but as the stress Q reaches a certain value, Q critical, suddenly the web buckles. So now the first question is, at what load or what stress this panel will buckle under compression. Okay. So for this we need to go into what is called as plate buckling theory. Now we have seen column buckling, we have just studied about beam buckling laterally and all. So plate buckling is quite similar, only thing is the plate is a two-dimensional member. So the equation will go into the fourth order, but once you solve that, similar to column buckling, you get a nice equation for buckling stress. So in column buckling, the stress is given by pi square E by L by R bracket square, right? So it is inversely proportional to the square of the slenderness ratio. In plate buckling, you get a similar equation where there is a constant K. This is actually similar to the KL, that you use a equivalent slenderness ratio, right? So this is for end conditions, Ks. It's also S is to indicate that it is called a shear buckling coefficient. Okay, so it is Ks times pi squared E, which is similar to what you have in column buckling. by 12 into 1 minus nu square, where nu is the Poisson's ratio, because the plate is now under stretching and compression in the other diagonal. So there will be a Poisson effect coming and it will shrink. So that is the nu, which is 0.3 for steel. So this E and nu are material constants, and E and nu are fortunately independent of the yield stress of the steel. So once I say steel, it doesn't matter whether it's mild steel or high strength steel. E will be 2 into 10 to the power 5 and nu will be 0.3. So you don't have to worry about what is the grade of steel. So basically we find that the critical shear stress at which a plate will buckle is inversely proportional to, I can write this as 1 upon d by t bracket square, where d is the depth of the web and t is the thickness of the web. Okay. So it's inversely proportional to the what is called as the depth to thickness ratio of the web. Okay. So in columns we know it is inversely proportional to L by R. Here even L doesn't matter, it is basically d by t of the web. Okay. So that is what it is. So that is the stress at which this plate will buckle. Okay. This is for an ideal plate. Practical plates may buckle at some stress little bit lower than this. Okay. So now we need to understand what is the typical value. Now Ks is called the shear buckling coefficient, and for a plate which is having all four edges simply supported, a plate which is in shear having all the four edges simply supported, that means these edges cannot move out of their position, but they can rotate. Okay, that is, the edge can rotate, the plate will buckle, and you can see here this plate would have come outside, right? So obviously all these edges would have rotated to facilitate the plate at this point to come outside. Okay, so the plate is assumed simply supported along all four edges and under shear, and if C is the spacing of the transverse stiffness, so the panel aspect ratio, as we call it, is C by D. Okay, so if C is greater than D, then the Ks is given as 5.35 plus 4 into D by C bracket square. If C is less than D, then this is the value for Ks. Okay, so that is the shear buckling coefficient. So we just have to assume some C and then find out Ks, and once we know Ks, we will know at what stress a plate will buckle. Okay, so that is the critical buckling stress, and the actual shear stress will be the shear coming V divided by area and shear AV. So that is my tau. So if tau is less than tau CR, the plate will not buckle, but the minute tau reaches tau CR, the plate will suddenly buckle in shear. Okay, so that is what it tells you. So this has nothing to do with even the Fy of the steel. Okay, so QCR is an independent value, and if tau reaches, you can call it tau CR if you want. If tau becomes tau CR, the plate will suddenly buckle in shear, and this is a variation of Ks with the C by D ratio. If those two equations, if you plot, they plot like this. One equation will plot like this, the other equation will plot like this. So we find that Ks is fairly high if C is greater than D, and this is also advantageous for us, because if you want to use C less than D, then you may have to weld large number of stiffeners, which will be a tedious and uneconomical thing to do, because it may be cheaper for us to increase the web thickness rather than weld so many stiffeners. Okay, so generally we will try to use C as 1.5 times D, so that we will get a Ks value of around 7. Okay, so just remember this when we solve a problem. What happens when the plate buckles? Now, unlike column buckling, where once the column buckles, it can't take any more load, the structure may collapse. Whereas in plate buckling, once a plate buckles, it can still take higher load. Okay, so that's the photo I am showing in the in this slide number 6, is when at ultimate collapse stage. Okay, when it slightly buckles, nothing really happens to the plate, it continues to take extra load. Okay, so we don't have to really worry about this plate buckling, but we should know at what stress the plate will buckle, and we are going ahead and trying to understand what happens beyond the buckling, that is the post buckling behavior. Okay, so what happens is the compression diagonal is unable to resist any more loading beyond the elastic critical stress, but it continues to take the load corresponding to tau critical. Okay, so the compressive diagonal continues to take a force compression which is corresponding to tau critical. Any further increase in the shear load is supported by a tensile membrane field anchored to the top and bottom flanges and adjacent stiffener members on either side of the web. So let's go and see what happens here. Now this diagonal takes a load corresponding to tau critical. Now this tau is more than tau critical, so that extra value tau minus tau critical is resisted by a pull along the membrane, that is along a certain width of the plate, which is going from one corner to the other. So this pull will try to pull both the flange and the web downwards here and upwards here, and if it is adequately anchored, that is if this corner is not easy to move or this corner is not so easy to pull in, then the plate will take extra load. Okay, so people have tried to find out how much extra load it takes, and they have found that if interestingly the extra load that is taken can be obtained, or the extra tau that can be taken can be obtained as the total state of stress in the web plate may be obtained by superimposing post buckled membrane tensile stress on the critical shear stress. So I'll get tau critical plus tau what is called as the tension field stress or action. Okay, so that field which is pulling our membrane is called the tension field action, and that is the tau TF. So that is how we can still calculate the load at which the plate, how the plate takes the load. Okay, so this shows how the membrane stress develops or the tension field develops, and it pulls the top flange, it pulls the stiffener, similarly it pulls the left stiffener and the bottom flange upwards. Okay, so that is how it, and its direction may be inclined. It will generally be, as we can see, from corner to corner, right? So that it will generally be along that direction. So this theta may not be 45 degrees. Okay, so that theta also we can obtain. Okay, so this is showing the tension field action, and the plate continues to take extra load. Now the next question is, at what load this will eventually fail? Okay, when load is further increased, tensile membrane stresses continue to exert an increasing pull on the flanges. Eventually the resultant stress obtained by combining the two reaches either the yield value of the web. So if it reaches the yield value of the web will start yielding, and even though the ends are anchored, it will start elongating, and that will be the end of the plate girder in taking shear, or the top and bottom flange will be pulled inwards. Okay, so we'll go back and see this figure. See here, the top flange which was straight, now it starts bending. So when I pull this, when this web pulls the thing, the top flange may yield here along this line, and then it will get pulled inwards. Okay, that is called as a collapse mechanism of the panel. So when that happens, also the plate can collapse, or that means that is the end at which. So here this is showing a side view. This is under this type of shear, anti-clockwise shear. So the tension diagonal will be this one, and when the tension diagonal is continuing to apply the downward pull, the flange which was straight like this, it will start yielding at this point and this point. So this point will be at a distance, let's say C or S from the corner. The code gives you a symbol S. So this distance can be calculated, and once we know that, we can actually find out at what load this collapse will occur, and that will be the ultimate load the plate can take. Okay, so and this width is called the tension field width. So basically that S is nothing but the sort of the tension field width. So that also can be calculated. So people have done enough research and given us simple formulas to calculate all this. Okay, so here you can see I have drawn a red line to indicate that somewhere here there is a kink, and the plate top flange comes down. There's another kink here, and then it goes this way, right? So this entire panel has now buckled as this is just a line or a very nominal stiffener which couldn't prevent buckling of individual panels like this, but two consecutive panels have together buckled, and the tension field cuts across them. Okay, so this distance is S, and that can be calculated, and we can actually tell at what load this collapse will occur. Okay, so basically there are now three phases of tension field action. The first one is the pre-buckling stage, three phases of shear resistance. First is the pre-buckling stage, second is the post-buckling stage where a tension field develops, and third is the collapse stage where a collapse mechanism develops. Okay, so all these calculations are possible. Now the code gives you two methods. One is a simple method where it says that you calculate only up to here, the point at which it will buckle, and you don't have to calculate the tension field. So this is called a simple post-critical method. The other method is to calculate right up to the end, including the tension field strength. So that is called the tension field method. So two methods are given. We'll limit ourselves to the simple post-critical method. Okay, so we will have to only calculate the critical buckling stress tau critical using the formula, and then convert that is for an ideal plate. So we'll have to convert that into tau b for a practical plate. So similar to columns, beams, plates also buckle at stresses lower than what is given by the formula, what is given by the theory. Okay, so that we have to incorporate. We'll see how to do that. So ultimate behavior of transverse web stiffener. Now the transverse stiffener play an important role. First is by increasing the web buckling stress. So what they do is they cut the plate into panels. Like let's say if I had not provided this stiffener, this would have a buckle from this corner to this corner, right? So they cut the length or the depth of the panel, and then as a consequence increase the tau critical. So if I provide C transverse stiffener at a spacing C, my Ks will increase depending on what C I am producing, and as a consequence of increasing Ks, my Q critical will increase. Okay, so that is what that is the major role that they play. But they also have two more roles to play. One is they anchor the tension field. So let's look at that slide. They support the tension field after the web starts buckling. Okay, so that is a second role. Then third role which they play is because they are in between the top and the bottom flange, they prevent the tendency of the flanges to get pulled towards each other. So they basically play three roles, and to play these three roles, the stiffener should possess sufficient rigidity to ensure that they remain straight while restricting buckling to individual web panels. So stiffener design becomes very important. Okay, so this shows how the stiffener is cutting this aspect ratio. It is also resisting the tension field, and it is also, this is the pull of the top flange. So this stiffener will make sure that this pull is taken partly by the stiffener, and it doesn't allow the top flange to come down. Okay, similarly this pull will pull the bottom flange up, so the stiffener will prevent that. So those are the roles played by the transverse stiffener. Then sometimes, as I said, we can also provide a longitudinal stiffener, because when you apply bending, the upper part of the web above the neutral axis goes into compression, and it may buckle out of its plane. So let's say this is an I section, this is the bottom flange. We are looking at it slightly from below, so we can see the entire bottom flange, and the longitudinal stiffener may be put in the compression zone or along the neutral axis, right, at the middle of the depth of the web. Okay, so this will not have a major role, but this will have a major role. This only makes sure that this panel size is further cut down into a smaller panel like this, because if the stiffener is not there, this panel will buckle at some shear stress, and that will be the buckling strength of this plate girder. So we want to increase that by putting one more longitudinal stiffener. Okay, so those are the three roles that they play, and when one of the sub panels buckles, we say that the plate girder has buckled. Okay, so that is a longitudinally stiffened plate girder. Now how does the code help us in calculating the stresses, shear stresses at which the buckling will occur and post buckling will occur? So we'll look at section 8 point of the code. We have seen already yesterday that for yielding in shear, you get Vp given by this formula. This we saw yesterday, but now our Vd is going to be less than what is given by Vp by Vn is Vp or Vp by gamma m naught, right? So our Vd is going to be less than that. It is going to be V critical by gamma m naught. So how to calculate V critical is the second. So 8.4.2 we go, resistance to shear buckling. So the code says a web panel will buckle in shear before yielding when d by Tw is greater than 67. Okay. If d by Tw is less than 67, it will yield. So you don't have to calculate the shear buckling stress. So you can directly use this equation. Okay. So only when d by Tw is greater than 67, we must calculate the resistance to shear buckling, and that is given by this. So this is basically Vn, instead of being equal to Vp, it becomes equal to Vcr, and Vcr is given by the area of the web, d into Tw into tau b, where tau b is the critical buckling stress, okay, for a practical plate. So how to calculate tau b is now the next issue. Now tau b is again a function of the slenderness of the plate. By slenderness, actually here we mean d by Tw of the plate. So we'll see that. I'll show you lambda w is given as Fy by √3 tau critical, where tau critical is a inversely proportional to square of d by Tw. Okay. So if d by Tw increases, lambda w will increase, and if lambda w increases, tau b will decrease. Okay. So basically the theoretical buckling stress that we derived as tau critical is as this formula, Ks into pi square E by 12 into 1 minus nu square or mu square, or mu and nu are Poisson's ratio. This one, this tau critical graph will plot like this, and for any plate, obviously tau y will be the tau y equal to Fy by √3 will be the yield stress. So we can say that for large slenderness, the buckling will govern. For smaller slenderness, yielding will govern. This is for an ideal plate. But for practical plates, there are three zones. When lambda w is less than 0.8, the plate will yield and collapse. So if you put d by Tw 67, you will get lambda w around 0.8, and you will find that you don't have to calculate the critical buckling strength. It will fail by yielding. When lambda w is between 0.8 and 1.25, what will happen is the plate may reach tau y, that is, it will yield in along one line, but before it can develop the full shear resistance, it will buckle. Okay, so it has this called inelastic buckling at intermediate slenderness range, and it buckles along this curve, and for that the equation is given in the code in terms of lambda w, tau b as a function of lambda w. If the plate is having high slenderness, lambda w greater than 1.25, it buckles along the theoretical tau critical. So tau b is same as tau critical, but the code, instead of writing in tau b as directly tau critical, it has given as 0.9 times this one. Okay, so we can find that out, and we'll find that we will get for lambda w greater than 1.25, tau b will be same as tau critical. Okay, so we have three ranges for tau b. And once we find tau b, we will know what is the total shear V critical at which the panel will buckle. That will depend on the size of the plate. Okay. So, and Ks is of course a function of C by D of the plate. Okay. So that's a simple equation. This is the tension field method, where WTF is called the width of the tension field and phi is the inclination of the tension field. So I don't want to go into this details, but basically I want to say that the tension field method gives you the strength as the critical strength. We can call this as V critical, that is tau b into dTw, we just saw that, plus an additional strength coming due to tension field action. Okay. So in the simple method, we are limiting ourselves only to the first term. In the tension field method, we try to go beyond that and calculate what is the strength that is available up to collapse. Okay, so that is the method is given here. We are not going to use it now. It's slightly beyond the scope of a UG syllabus. Okay, so design of beams and plate girders with solid webs. When d by tw is less than 180 epsilon, and c is greater than d, so when transverse stiffeners are not provided, the code says you limit your d by tw to 180. Okay, and when transverse stiffeners are provided, you can go beyond 180 up to 200 if c is greater than d, and up to 270 if c is less than 0.74 d. Now these are very uneconomical designs. So as a thumb rule, I will say try to keep C as around 1.5 times D. Okay, so it is greater than this, but less than D, this one, but that also we are not using. We will use this. Okay, C is around 1.5 times D. So up to 200 we can go D by TW. Okay, and when transverse and longitudinal stiffeners are provided, you can go further high. And when a second longitudinal stiffener is provided at the neutral axis, we can go up to D by TW of 400. So just to give you an idea, let's say a plate, web of the plate is 2 meters deep. So I can use a thickness for 2 meters, that is 2000 by 400 will give me 5 mm. I can use a 5 mm thick plate similar to a wall, and which is almost 2 meters deep if I am providing stiffeners. So that is the values up to which we can actually design plate girders. But generally people do very conservative designs, they use very thick web plates. Now just to summarize the design procedure, initial sizing of the plate. Like yesterday I told you that any beam design has to pass serviceability limit. So to ensure that it will pass serviceability limit, you should keep the depth such that L by D is between 12 to 20. Okay, so we will keep it around, let's say 15, and calculate the minimum D and provide suitably, right? So generally plates are available in let's say around in thicknesses of 4 mm, beyond let's say 12 mm. After 12 I'll have 16, after 16 I'll have 20 mm thick plates, then 24, 28, 32 and so on. And similarly depths are also restricted in terms of 200 mm. So we should try and use, so that we don't have to cut some plate unnecessarily, right? That will be extra work. So we will round it off to the nearest let's say 200 mm value, right? So after let's say 800 I can use 900 also I can use, but I can use 1000 also. So I'll prefer 1000 instead of 900. So I'll keep that as my depth. Okay, that when I say provide a D suitably, I'll use nearest rounded off value. Then calculate the area of flange required by, because area of flange into Fy by gamma m naught is the force in the flange, then T or C. So in plate girders generally we neglect the contribution of the web to the bending resistance, because web is very thin. By neglecting that we are not losing much, but then we are getting a economical design by going for a deep girder. And also we should try and make sure that the flange is plastic, so that this, even though we are not designing by tension field etc etc, this mechanism has a chance to develop. Okay, that is, this will develop only if the flange is plastic. Otherwise what will happen is, before coming to this point, between this or even here, the flange may locally buckle and the plate girder will not reach this. So it will buckle earlier, okay, and fail. So to avoid that, generally you should use plastic flanges and slender webs. Web slenderness will be around let's say 150 to 200. That is D by TW should be around 150 to 200, and based on that we are calculating, if the bending moment is Bm, we are calculating AF required as Bm by the depth which we arrived at here, we put here, divided by Fy gamma m naught. So we'll get AF required. So now area of flange is nothing but width of flange into thickness of flange. So I need to know at least one to choose the other. So to avoid lateral buckling, I choose BF as a thumb rule to be around 1/3 of the depth of the flange. Okay, so we saw in the previous lecture that if the girder is narrow and deep, the flanges are not so wide, then lateral buckling will be an issue. So we keep flanges sufficiently wide. Okay, so BF taken as, let's say, around 1/3 of D, and depending on whatever number comes, we'll round it off, and that will be the flange width. And that once you have AF and you decide BF, AF by BF will give you the thickness of the flange. So again, thickness of flange may come, let's say, like 7 mm means you can use 8 mm plate. If it comes 9 mm, you use 10 mm plate, and so on. Okay, so 9 is not available. So after 6, 5 is available, 6 is available, 8 is available, then 10, 12 and 16. So these are the thicknesses that are generally available, and you will find that you wouldn't have to normally exceed 12 mm thickness for most designs. Okay, so check that the flange criteria gives a plastic section. So B by TF should be less than 7.9. Web thickness should be between, D by TW should be between 67 and 200. So choose such that TW is greater than this value, so that this will come below 200. And check the flange buckling into web. This code gives you one more clause, so that can be checked. So for that we use C greater than 1.5D. Then check the shear capacity of the web. So V is now Vn, basically given by AF Fy by √3 or VCR. This will generally not govern, so VCR has to be checked. And for calculating resistance to shear buckling, we need to get Kv as a function of C by D. And once I get Kv, I'll get tau critical, and based on that lambda critical, I'll get tau V, and that will give me the VCR. Okay, if the shear coming in the web is less than VCR, then the design is safe. Otherwise, either you can go for tension field calculation, or you have to reduce the stiffener spacing, or you can increase the web thickness. One of the three, until you get a safe design. Okay, so web has to come safe under the shear that is coming on the web. Okay, so that completes the cross section design for a plate girder. So 10 steps are there. Then you go for providing the stiffeners. So stiffeners are again basically to prevent shear buckling of the web, we use intermediate transverse web stiffener, ITS. To prevent other types of web buckling, we may use load carrying stiffener, or web crippling we may use bearing stiffener, etc., etc. And for stability at the ends, we may use a torsional stiffener, and so on. So there are a variety of stiffeners. These are defined in the code, and generally one stiffener can perform more than one role. Okay, so at the support, I'll have a stiffener which not only contributes to web shear strength, it also takes the vertical reaction from the support, and it also prevents web crippling. So web buckling, web crippling have to be prevented. So the same stiffener can be used. Okay, so now how to check web buckling? Yesterday we have seen in the first part of the presentation for laterally restrained beams. So similar procedure we use. There we were checking at 45-degree angle what is the B1 plus N1 we were taking. Instead of that, now we will take the stiffener, basically B1 is whatever we are neglecting. Basically we are taking 20 times TW on one side. Sometimes what they do in plate girders, they extend the web beyond the stiffener. So if that is the case, you can even take this also into account. Okay, let's say this is my stiffener and the web is extended beyond the stiffener. So I can take 20 TW this side, and whatever is the extension that I can take on this side, limited to 20 TW. Okay, so that I can take. And then this plus shaped cross section, that is, if I have stiffener on both sides, then it is like this, plus web on both sides. In many cases I'll have stiffener on one side and only web on one side. So this L-shaped cross section, whatever, that has to be now checked for buckling about the weak axis, this axis, center line of the web, and we need to make sure that it will take the load between the flanges. It will not buckle as a web buckling. Okay, so that has to be checked. Before that, the stiffener for preventing shear buckling of the web should have a moment of inertia. If C is greater than √2, then I provided about this center line, that is Bs minus Tw by 2 cube into T cube by 12. This is basically nothing but BD cube by 12. Okay, this is my B. E cube by 12. So I can actually neglect this. I can say moment of inertia of the stiffener about one of the edges. So it will not be very different. So 1/12 T cube BS cube is what is value of I provided. That should be greater than this value. Okay. So if that is the case, this stiffener will be strong enough to prevent the web from buckling across the stiffener. It will restrict buckling to each side of the stiffener. Okay. So it will not buckle with the web. That's what it means. So that is web buckling. And this is stiffener to prevent web shear buckling. Stiffener to prevent web buckling between the top and the bottom flange. We are providing such that we assume some depth of the width of the stiffener and thickness of the stiffener. We may even provide on both sides. And then this plus shape, imagine this is a cross section for a column. This has to be now checked for the applied load, if it's a point load, or if it's a reaction, the reaction at the support. So if the reaction at the support is V, the shear at the end of the beam. So we have to check that this stiffener has a radius of gyration Rxx such that, and a moment of inertia such that KL by R gives you some lambda, and for that lambda the FCD is into area of this cross section exceeds the load coming on the cross section. Okay, so that is how we check it as if it's a column buckling between the flanges. So effective length is 0.7 times the depth of the web. So that is the effective length between, that is the distance between the flanges, 0.7 times the distance between the flanges, and for that we are checking it as if it's a column. Okay, so that is how we should do. And then the shear connection to the web of the stiffener, you will have to do welding here and here. So the code gives you a formula. It says TW square by 8 BS is the welding that you need to do on the side of this. This is a dimensional equation. So if you just substitute TW in mm and BS in mm, you are going to get the shear in Kn per mm. Okay. So that 8 has some dimensions. It is not a non-dimensionless number. It's just not a number. So based on that, we'll have to do the welding. Similarly, we'll have to do the welding between the flange and the web. I'll just go back to one of these slides. So here what they do is, first they will weld between the flange and the web. This weld will run continuous, and the stiffener will be having a small cut here to accommodate the weld. So when I do the stiffener welding, my weld should not touch this flange web weld. Okay, so that is how it is done. The stiffener will be welded at the top and then on the side, and that is how the stiffener will be attached to the web. Okay, so all these welding also has to be designed. Okay, for completing the design of the plate girder. So that completes basically a design procedure. We'll actually do the calculations tomorrow for our example problem. I've also given one problem in the assignment as a cantilever plate girder. So you can ask, after solving the problem tomorrow, you can try and solve the assignment problem. But of course, in design, the solutions will not be unique. So you may get a correct design, but it may not match with my solution. So don't worry about that. As long as you are satisfying all the codal provisions, your design may be correct. Okay. So thank you very much. Now it's open for questions. 5 unknowns in prop cantilever beam. Okay, probably this is about yesterday's presentation. So actually there are no 5 unknowns. The horizontal forces are not applied on the beam. So there are no horizontal forces in the fixed end and no horizontal force in the propped end. Okay. So I have only 2 reactions at the 2 ends and 1 movement in the fixed end. So there are only 3 unknowns, and I have 2 equations. One is sigma V equal to 0. So that means, let's say we call the reactions R1, R2. R1 plus R2 equal to the total load on the beam. And the second equation is let's say the bending moment at the free end is 0. So I'll have M plus R1 into L, the span of the beam, okay, where M is the fixed end moment, plus with appropriate sign, the moment contributed from the applied load. So that should be 0 at the free end. So I have only 2 equations. So that is indeterminate to a first order, right? So I have one unknown left. So for that we can use a compatibility equation at the free end. Okay. So there's one more question which says in which case we will go for tension field method. So there are two requirements. One is the designer should be able to do the tension field calculations properly. So that is the first requirement. And if he can do that, then he will get a more economical design. Okay. So especially let's say your plate girder, you are assuming some web and you are checking and you are finding that it is just failing. Like let's say the plate girder is buckling in shear at let's say 1000 kilonewton, but the applied load is 1200 kilonewton something. So it is 20% more. Let's say around 10 to 20% more. Then either I have to reduce the spacing of stiffener, which will be involving some cost, or I have to increase the thickness of the web. That is also expensive. But if I can do the calculations for tension field, it may come out safe for 12,200 kilonewton. So that is when the tension field calculations can be done and the girder can be still shown to be safe. Okay, so that is the answer. How can we make the flange plastic? Basically by restricting the width to thickness ratio of the flange to the plastic limit, right? So if let's say 8.4 was the limit or whatever, then my B of the flange should not be more than 8.4 times the thickness. So if I am choosing some bit B for the girder, let's say 1/3 of the depth. Let's imagine the depth to be 900. So 1/3 of that will be 300. So my flange has become 300 mm wide. So the B for calculation of width thickness is 150, and 150 by whatever is that number, 8.4 or whatever. So thickness of the flange should be more than that. Then it will become plastic. Okay. So if it is not, then I have two options. One, I don't have to keep it 300. I still provide the same area, but I reduce 300 to let's say 270 something. Okay. So 270 by let's say the B by T value is 9. So I want to use 9. 270 by 9 will give me 3 mm thick. Right? No, 30 mm thick. Right? So that is how it will come. Okay. So I have to restrict that value. Okay, there's one more question. Flange is plastic and web is compact means how can we classify the section? So the section will be classified as the worst of the two, that is compact. So the section will be classified as a compact section. Generally the D by T limit for neutral axis at mid depth is around 42 for webs. So once you cross 42, web becomes slender, but in plate girders slender webs are allowed. Okay, except for that no other place slender webs will be allowed. Okay, if there are no more questions, we will close for today. Thank you.